Hi, and welcome to a video on constructing a third order Taylor polynomial for f of x equal 2 to the x, and we're going to center this Taylor polynomial at x equals 1. So the first thing we're going to do is we're going to write down our template for our Taylor. Since it's a third order, we're going to do t sub 3, just indicating that that's a third order. And we are going to write our coefficients, so a naught plus a sub 1, and since we're centering at 1, we need to do a horizontal shift right 1 unit, so you're thinking of these as horizontal shifts, plus a sub 2 x minus 1 squared plus a sub 3 x minus 1 to the third. And right here you can see we've got our third power, which is the same as the third order. All right, so now we need to go ahead and focus on our function and how we're going to use this function to write our Taylor polynomial. So when we're doing this, we always start with our function, f of x equals 2 to the x, and we need to take derivatives all the way down to the third derivative. So let's go ahead and do that quickly. Now, as you're doing this, you want to make sure you recall the derivative of an exponential. So just as an aside, recall that the derivative with respect to x of a to the x is a to the x natural log of a. So as we're doing these problems over here, if I'm taking the derivative of 2 to the x, that's going to be 2 to the x times the natural log of 2. And then I need to treat that as the function. When I take the second derivative of x, I'm going to have that constant right here, natural log of 2, and then I'm going to take the derivative of the function times 2 to the x times natural log of 2. So that kind of tells us why we're getting these derivatives. So just a little aside, that's one that sometimes people forget. So that's just a reminder. All right, now that we've got all three of our derivatives, because we're doing a third order polynomial, we need to now evaluate each one of these at 1, because that's where we're centering our polynomial. So if we evaluate each one of these at 1, for the first one we're going to get 2, and so forth. So let's quickly evaluate those. Okay, now that we've evaluated each one of our function and three derivatives at x equals 1, we can go back and think about what our coefficient formula is. So if you recall, we have a coefficient formula that looks like this. A sub n equals the nth derivative at wherever we're centering it. We'll call our center in this case c, but for this problem our c is our x equals 1. And we're going to divide by n factorial. And then, after we've got each one of these coefficients figured out, then we can go back to our Taylor polynomial and put in the coefficients. So let's figure each one of these out. Okay, so for our a naught, we're going to do f evaluated at 1, which is 2, divided by 0 factorial, which is 2. A sub 1 is going to be f prime evaluated at 1 all over 1 factorial, which was 2 natural log of 2 all over 1, which is just 2 natural log of 2. I don't think I'm going to squeeze it in there. I'll write it down here. So that's just going to be 2 natural log of 2. A sub 2 is going to be the second derivative evaluated at 1 over 2 factorial, which is going to be 2 natural log of 2 quantity squared divided by 2 times 1. So those are going to cancel. So our a sub 2 is going to be natural log of 2 quantity squared. And then our very last one, a sub 3, is going to be our third derivative evaluated at 1 divided by 3 factorial. So we're going to have 2 times the natural log of 2 cubed divided by 3 times 2 times 1, and the 2's are going to cancel again. So our a sub 3 is going to equal 1/3 times the natural log of 2 quantity cubed. And now that I have all of my coefficients, I can go ahead and put my Taylor polynomial together. So let's go ahead and write our Taylor polynomial. t sub 3 of x is going to equal a naught was 2 plus, and I'm going to put the rest together for us here, just grabbing these coefficients that I figured out over here. All right, here we go. All right, so there we have our Taylor polynomial, and don't forget your exponent on that last x minus 1 quantity cubed. All right, and let's go ahead and see how this graphically looks or compares to our original function, so you can kind of see the whole purpose of doing this. All right, as you can see here, I have graphed just our original function on Desmos, and I am going to show you how when you build your Taylor polynomial, as you go up in successive orders or successive degrees, your Taylor polynomial becomes a better match for your original function. So if I build just a t equals 2, you can see here it matches my function exactly where we're centering it. So this function is only going to match our function exactly at 1, which is where we centered it. If we build a first order Taylor polynomial, you can see that green line, that linear function, is a match. It also is going to be exact at our center, which is 1, but it's going to fit a little bit better. So our error is going to be very small as we go slightly to the left and slightly to the right of 1. I'm going to turn off our 0 so we can kind of see as we compare. So the second degree or second order should be an even better match than the first degree, and you can see that it is. You can see here that purple function matches better than the green as we get closer to 0. And then that third order, which is the last one, the black line here, you can see it fits very well until we start getting close to -1. It looks like it pulls away from our original function. So if I kind of back out, you can see that last one that we just did, that third order Taylor polynomial is a rather good fit for our function from about -1/2 all the way to about 3-ish. As we get closer to 3, it starts to pull away. So this is just a visual of what we did analytically so that you can compare the two. So I hope this video helped you to better understand how to build a Taylor polynomial and then what we use a Taylor polynomial for, what it actually represents with respect to our original function. Thanks for watching.